In this lecture, we derive this long exact sequence in homology using spectral sequences. So you start with a map of chain complexes like this, A, B, C, and this gives rise to a long exact sequence in homology like this. So Hn A, Hn B, Hn C, then Hn minus 1 A, Hn minus 1 B, Hn minus 1 C, and so on. So we will give a proof of this using spectral sequences. So note that we have already proved for topological spaces for pairs like A contained within B and then C is just B modulo A, that we have done. Here we will do for this case where we just have chain complexes like this. So first we start with the map. You make a double complex like this. You have, and this is the chain complex B, this is the chain complex A, and this is the chain complex C. And these are the maps. These maps here are here. We are just writing the maps so that it is consistent with page 0 notation for the spectral sequence. So you have zeros going in here and zeros coming out here. Similarly here. So these are all short exact sequences. So this green arrows and these are all short exact sequences. So these are all short exact sequences. This is short exact, this is short exact, and so on. So if you use your filtration by rows, or you can say your vertical filtration, then you see what you have is just exact sequences. So therefore our final page or our page, what we call as page infinity, using our row filtration or vertical filtration, means that this page will just consist of zeros. So final page just has zeros. So at every place in the final page you just have zeros because you have exactness here, and spectral sequence is all about taking homology groups. So you take homologies here, it will all be 0. So now we start taking homology in the vertical direction. So now we are going to work with the column filtration. So just look at the columns and we start with page 0. So for page R you move minus R, R minus 1. So page 0 you will move 0 minus 1. So 0 left, 1 down. So therefore all the arrows are facing down. So this is our page 0. So now we start computing homology here and putting it on page 1. So page 1 is right here. So you compute homology here, it is H3C of the complex. This is H2. Here will be H1. This will be H0 of C. Then here corresponding B, H3 of P, H2 of P, H1 of P. And again you're computing the homology corresponding to this chain complex and you're putting it right here, H3, H2, H1, H0. Now what about the arrows? So we are on page 1. So you put R as 1 right here. So you get minus 1, 0. So you have 1 left, 0 down. And that's why the arrows are going 1 left. So you put this arrow as partial 3 and this is D3. This is partial 2, D2. So this is our page 1. So from page 1, now we will go to page 2. So now we rewrite our page 1 like this. So we have just copied the page 1 from the previous slide. So this is our page 1, but everywhere else, these are only non-zero entries. Everywhere else on the page you have 0 entries. So you have zeros like this, and then you have zeros here. So you see zeros are coming in, zeros are going out everywhere. So now for the next page, so this was page 1. For the next page, we start taking our corresponding homology. So homology here would be just be kernel of this D3. So kernel of D3. Homology here would be co-kernel of partial 3. So this is co-kernel of partial 3. And homology here is kernel of partial 3 over image of D3. So that is what it is. So we keep writing it. So again, homology here, because this is going out to 0, everything is in the kernel. So H2C over image of partial 2, which is nothing but co-kernel of partial 2. So co-kernel partial 2, co-kernel partial 1, co-kernel partial 0. Similarly, you have kernels here, kernel D2. And here you're just using the definition of homology, kernel of delta 3 over image of D3. So that is what it is. So now notice that on page 2, again our convention is minus r minus 1. So on page 2 you will be minus 2 1. So 2 left 1 up. So you go 2 left and 1 up. So these are the arrows which are going up. Everywhere else we have zeros. So you have 0 here, 0 here, 0 here, 0 here, 0 0 0 0. So notice that for here there is an arrow which is coming from 0 and it is going out to 0 as well. So the only arrows going from non-zero to non-zero are these arrows which we have drawn in white. So first thing you observe is this. So we will be stabilized after page 2 because the arrows are going to get longer. You're going to get 3 more left. So then this will just hit zeros all the time. So everything will stabilize after page 3. And we know things have stabilized after page 3. So page 3 is going to look exactly like page infinity because there is going to be no change after page 3. And page infinity just has zeros everywhere. So that means page 3 will also have zeros everywhere because page infinity has zeros everywhere. So if page 3 has zeros everywhere, that means this group, this is already stabilized. 0 is going in and 0 is going out. So this is going to be the same on page 3. But page 3 it has to be 0. So that means kernel of delta 1 is equal to image of D1. Similarly here, kernel of delta 2 is equal to image of D2. So this is the exactness in the middle. Kernel is equal to image. So this kernel of this map is equal to image of this map. So we have exactness right here. So we have been able to construct some kind of an exactness in the center. Actually, we have been able to construct an exactness like this. So all these rows with white arrows are exact, but still we can't say anything about here and here. So now this is not exact. So say there is no exactness at this part. There is exactness in the center here. There is exactness here, which we have just shown. There is no exactness here and there is no exactness here. So we can make this a short exact sequence by making exactness here by putting a kernel here. So if you put a kernel here, this becomes injective here, and you put a co-kernel here, this becomes surjective here. So you can make something like this. And this co-kernel is precisely this map. This kernel is precisely this map. So now we are going to glue this portion with a portion here. So going in, we can always put kernel of D1 here. And we can glue this with this. So if we glue these two, we will get a map which goes from here to here. So we want to glue this kernel of partial 2 to kernel of D1 so as to get this snake map or our delta map. So this you can only glue them if this co-kernel of delta 2 is equal to kernel of D1. But this will hold because on the next page, whatever homology you compute will stabilize and it has to be 0. So it has to be the case that these two are isomorphic. So this is isomorphic to this so that no homology remains. So in general, you're saying kernel of D1 is isomorphic to co-kernel of delta I plus 1. So let us just see this map in again, how gluing these two actually leads to this delta map. So say we have an exact sequence like this and we have another exact sequence like this, and these two are the same. If these two are same n, you can glue them together to get a sequence like this. And what we are talking about is that we have this map here. This we already shown exactness here, and then we make this was not exact. We make this part exact by putting in co-kernel of say partial q here, and then you have this map hq minus 1, and then this will go to hq minus 1 of our complex in B, and so on. Similarly, n equals to n, you can glue these two together to get this long arrow. Just like here, you can glue these two together, this mi minus this is here. So you can glue these together to get this long exact sequence, and this is our connecting homomorphism delta.